5 rectangles, we can do that. So then we created a math program to add all these this change in x, 1, 2, 3, 4, 5, to x sub n. So we can have this many x sub n rectangles underneath that curve to find the area.
Sorry.
So what we want to do, guys, is we're actually finding the limit as n approaches infinity of the summation of this function, And the x is changing. X sub 1, x sub 2, x sub 3. That's why we put x sub I, because it's the summation of all those areas of the rectangles, all right? And times the change in x. So this is just the area of each base times height. Or it's actually base times height, all right? Base times height. And what we do is this converts to our integral right here. This is our integral. This is our lower bound and our upper bound of the function f of x dx. So this is the area of each rectangle. We sum them up to give an approximation, where we get better approximations as you take the limit as x approaches 0. And that's like just the core idea of integral calculus, where we can get a big, large sum and do it in one simple step, is what they're trying to simplify it with, okay? So theorem 1 is the existence of definite integrals. All continuous functions are integrable. So all continuous functions are also what? What's the opposite of integration? Differentiation, right? So if we have a continuous function, is it differentiable at all spots? Sure, because it's continuous everywhere, so it's differentiable. So it's the same thing for integration. So if you have a function that is continuous over an interval, then the definite integral also exists, okay? That definite integral also exists. So what we have is our conversion. What this really means, this integral right here, this means that we're taking the limit of a summation of the areas of rectangles. You guys understand that? So integration is taking the limit as n approaches infinity of the summation of the areas of rectangles. That's really all it is. Okay? That's what integral calculus is. So what we do is this change in x is our upper bound minus our lower bound divided by the number of rectangles we're going to have. So what we programmed in the calculator, we programmed this. This is what we put in, the change in x. Okay, the upper bound minus the lower bound. And if we look here, here's our upper bound and lower bound. You see our upper bound and lower bound. That's where we're finding the area of the curve. Do you guys see that? So it's this minus the upper bound minus the lower bound divided by however many rectangles we're going to have inside of there. So when it asks for how many intervals, and you put in 50, 100, 1,000, you put in that number in there, that's the n. Okay, that's the n. It's going 3 minus 0 divided by n. 500. 3 minus 0 divided by 1,000. You guys see that? Okay, that's what that program is doing. Let's see here. So yesterday, this is the video that we watched a little bit with the Khan Academy video, and it's just talking about how we have we have a positive area and then a negative area, and then we also can have our areas here where we add them, we kind of combine them together, and if it's a greater area, then the whole area will be negative. And and if it's a greater area and positive, then the whole area will be positive. You guys see that? So they'll just kind of cancel each other out a little bit, but not really, because it's still the whole area, but the whole area is gonna be either positive or negative. It depends on which is greater, okay? It'll be dependent on which is greater. So this is just an up-close example of what we have. Okay, let me go to the next one. Let's work some examples, all right? All right, so in your book, we are going to use our notation, all right? So get your marker. We're gonna look at number 1, and then you guys will do the rest, okay? So for number 1, all we're gonna do is we're going to convert from our limit notation, our sigma notation, summation notation, to integral notation. That's all we're gonna do. We're gonna convert this equation here to integral notation, okay, to integral notation. So what we're gonna do is we see that we're gonna express it as a definite integral. So we have this c sub k, let me lower it just a little bit. When we have c sub k, then this represents our f of x. This is our f of x right here. And so we see that if it's c sub k squared, then we know that f of x is equal to x squared. So we put, if f of x is equal to x squared, then we can throw that into our integral. F of x squared dx, and then there's our lower bound and there's our upper bound. So that's all we're gonna do there is the lower bound and upper bound. So you guys try number 2 in the book. Let's try number 2.